This is a video lesson on a concept called stoichiometry. And stoichiometry is the quantitative analysis of your chemical reaction. So, of course, with our chemical reaction, when we have it balanced, we're looking at these mole values when we have our equation balanced, and that's referred to as our mole ratio. And that mole ratio is going to be important when we do chemistry, when we actually do chemical reactions, and knowing the quantitative or how much we're going to be measuring out of our material or how much will be produced. And because these are all based off of chemical changes, I'm going to show you this quick little video to hopefully motivate you with chemical changes. It's pretty fun.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium.
Okay, so those are chemical changes. And with the chemical changes, we're going to write a chemical equation. We're going to balance that chemical equation. And based off of the balanced chemical equation, we're going to look at this chemical equation in what are called the mole ratios. And what's so fantastic about doing that is that it allows us to look at how much material we're either going to be reacting or how much material we're going to be producing. So let's get started with looking at stoichiometry.
Mercury 2 oxide breaks down or decomposes readily when heated. If we were to weigh the compound before heating and compare its mass to that of the mercury remaining after the reaction, it would seem that decomposition causes a change in the system's mass. The product mercury would weigh less than the reactant. In reality, the decomposition liberates the reactant's oxygen atoms as gaseous dioxygen O2. All matter present before the reaction still exists after it. The reaction obeys the law of conservation of matter.
So in this reaction, we have a balanced equation written, and that is 2HGO producing 2 hydrogen and 1 oxygen. And that relationship we can look at in terms of a mole ratio. So that would be 2 moles of mercury oxide to produce 2 moles of mercury and 1 mole of oxygen. If we wanted to use applications of that where we would measure out these quantities, what we would use is the molar masses. And those molar masses come from the periodic table and those atomic weights or atomic masses that we have, and mercury being 200.59, oxygen being the 15.9994 or 16, we can look at the molar mass of mercury oxide to be 216.59, mercury to be 200.59, and oxygen to be 32. So in applications of what's called the mole ratio, we could actually too have what's referred to as a gram ratio. And that is taking the mole value, so the 2 moles of mercury oxide, multiplied by the 216.59 to get the 433.18 grams of mercury oxide to produce the 2 moles of mercury, which is 2 times 200.59, so that's 401.18 grams of mercury, and then 1 mole of oxygen, which is 1 times 32, so of course that's 32 grams of oxygen. And as stated on the video, the concept of mass, or the law of conservation of mass, holds true. The reactant mass, which is 433.18, is equal to the product mass. So if we add together the 401.18 plus the 32, we get 433.18. So that shows that the atoms are equal on both sides of the equation because the mass is equal on both sides of the equation. This is another example of a decomposition reaction, but in this case it's going to be hydrogen peroxide. And it's a pretty interesting reaction because hydrogen peroxide decomposes so quickly. And when you add a catalyst, and in the case that you're seeing sodium iodine is being added, the catalyst doesn't change in the reaction, it just helps initiate the reaction. It produces a gas, it actually produces 2 gases. So we're going to write out that equation. And if you want to follow along, this is on page 196. So we're looking at the decomposition of H2O2. And when H2O2 decomposes, it decomposes into water vapor as a gas and then oxygen also as a gas. When we go to balance this equation, we want to balance it with our coefficients by putting a 2 in front of the H2O and then a 2 in front of the H2O2 and then a 1 in front of the O2. So that balances out 4 hydrogens, 4 hydrogens, 4 oxygens, and 4 oxygens because the oxygens are spread out. So we have our reactants and we have our products. Now again, those coefficients represent a mole ratio. So we can say we have 2 moles of H2O2 reacting to produce 2 moles of H2O plus 1 mole of oxygen. And then we want to look at what's called the molar masses, right? Those numbers from the periodic table, those atomic masses. And what we're looking at is, in this case, hydrogen having the 1.01, I'll round that to 2 after the decimal. And then with the oxygen, which is 15.999 or 16, I'll round that one as well. Okay. What we're going to do is use those to write the molar masses of H2O2, H2O, and O2. So we're going to use the molar masses to hopefully get what's called the gram ratio and see that equal mass of the reactants to the products. So for H2O2, we're looking at 34.02 grams per mole. So that's our molar mass for H2O2. For the H2O, that's 18.02 grams per mole. And then for the O2, that's 32.00 grams per mole. And what we'll do now is use those molar masses to go from moles to grams in this equation. So I'm going to take my 2 moles, multiply it by the 34, and that will give me 68.04 grams, and this of course is grams of H2O2, the dihydrogen dioxide or hydrogen peroxide, H2O2, and then the next one is 2 moles of H2O times 18.02, so I'm going to multiply this relationship, and that will give me 36.04 grams of H2O. And then in the last case with the O2, 1 mole of O2 will produce 32 grams of O2. And let's see if this keeps that law of conservation of mass. So does my 68, right here, my reactant mass, the 68.04, does that equal adding up our product mass? So 36.04 plus 32, yes, so that would be 68.04 grams. So that's our law of conservation of mass, and it works in looking at your mass ratio of your balanced equation. Okay, so we're going to start with looking at the stoichiometry problems on page 198, and we're actually going to work on them 198 to page 200. And on those pages, you're going to see with the stoichiometry that I actually have 4 different stoichiometry type problems that we'll be looking at. The first type that we'll look at is when you'll be given a mole quantity of one material, you want to find the mole quantity of another material. So that's one type of stoichiometry problem. The next type of stoichiometry problem is where you would be given given a mole quantity of one material, you want to find the gram or the mass quantity of another material. And then the third type is where you'd be given a mass or a gram quantity of one material. You want to find the mole quantity of another material. And then the very last type of stoichiometry is where you're given a mass quantity of one material. You want to find the mass quantity of another material, or the gram quantity. So those are the 4 basic stoichiometry problems that we're going to be looking at. So the first problem involves going from a mole of A to a mole of C. So moles of one material to moles of another material. And the reaction we're looking at is Fe2O3 plus 3H2 to produce 2Fe plus 3H2O. And the question states how many moles of hydrogen, which is the H2, are needed to react to produce 15.65 moles of the iron. So what I like to do when I approach a problem like this is to first identify what's being given. So in this case, it is the 15.65 moles that are being given. And then I like to highlight what's being asked. And what's being asked is moles of hydrogen. And then I go to the balanced chemical equation and I highlight those two things. So here's my iron and here's my hydrogen. So from there I can do the calculation. These, the two that I highlighted in the chemical equation, remember those are referred to as the mole ratio. So I can say, 3 moles of hydrogen and 2 moles of iron. And I'm going to use that relationship to do this calculation. So to set this up, I'm going to start with my 15.65 moles of Fe. That's given. And then I'm going to multiply that by the balanced equation relationship. And I'm going to multiply that by 3 moles of H2 over 2 moles of Fe. And I set it up like that for a couple reasons. One, it allows my units to cancel. So this allows my units of Fe to cancel with my units of Fe there, and I'll be left with moles of H2. But I also set it up like that because this is referred to as the bridge step. And the bridge step is when you go through and use your balanced chemical equation in that mole ratio and setting it up like a bridge where I put 3 moles of H2 because that's what I want to find over the 2 moles of Fe because that's what I'm kind of leaving or dividing out. So by doing this calculation, I get the answer 23.475 or 23.48 moles of H2. And that would be the answer of this stoichiometry problem where you're given a mole quantity, find a mole quantity. So you just set up what we refer to as this bridge step. Okay, so now you try the next 3 on this page and see if you can set these problems up with that same format. Okay, so now for the next example. In this example, we're looking at the reaction between aluminum and chlorine. And this is a given mole quantity, find a gram quantity. And this question says how many grams of Al2Cl6, so I'm looking at trying to find the grams of Al2Cl6, are produced when 0.144 moles of chlorine are reacting. So I'm given 0.144 moles of chlorine. So it's the relationship between Al2Cl6 and chlorine. So I'm going between those two materials in this balanced equation. Well, I can do the same thing I did in the last example, but then I'm going to add on a step. So my first task is to get my quantities of moles of chlorine to moles of Al2Cl6. So I do want to do that bridge step first. So to start that off, I set this up where I write out the 0.144 mole Cl2, and I'm going to multiply that by the relationship of Al2Cl6 to chlorine. So I'm going to put 1 mole Al2Cl6 on top because that's what I want to find, and then 3 mole Cl2 on the bottom because that's what I'm converting from. And the answer to this calculation gives me 0.0480 moles, and this of course is moles of my Al2Cl6. Let me write that again. So my Al2Cl6. And I can end there if moles of Al2Cl6 were being asked, but grams are being asked. So what do I need for this equation, or to solve this problem? I actually need the periodic table, and I need molar masses. And the molar masses I need are of the Al2Cl6. So I need to look at the atomic mass of my aluminum, which is 26.981, and the atomic mass of my chlorine. Add that together to get my molar mass of Al2Cl6 so I can do the next step. Because in the next step, what I need to do is take the answer from the first step, so the 0.0480 mole Al2Cl6, and I'm going to multiply this by the molar mass. So I want to set this up where by adding up the Al, the 2 aluminums, and the 6 chlorines, I'm going to multiply by that molar mass. And that molar mass calculates out to be 266.68, and that would be grams of Al2Cl6 over 1 mole Al2Cl6. So that's my molar mass. Okay, and I set that up again, my units cancel, and I'll be left with the mass quantity of Al2Cl6. So I get an answer of 12.8 grams, and that of course is grams of my Al2Cl6. And that's my answer. So just to kind of quickly review what was done with this problem, my first task was to figure out the mole quantity using my bridge step. So I took 0.144 moles of chlorine, multiplied it by the coefficient ratio of Al2Cl6 to chlorine, and that provided me with the mole quantity of Al2Cl6. And then my next task, which I did in blue, I take that mole quantity, I use the molar mass to find the gram quantity of Al2Cl6. And that's how I tackle that mole, given mole, find gram relationship for this problem. Okay, so now pause the video and try the next 3 on this page, which involves doing a mole to gram conversion. This next example is doing a calculation in stoichiometry where we're going to be given a gram quantity of one material, find the mole quantity of another material. And in this calculation, it involves 2 hydrogen plus 1 oxygen to produce 2 water molecules, or 2 moles of water. So we're looking at a question that says if 45,450 grams of oxygen were put into fuel cells to react with enough hydrogen, how many moles of water is produced? So this is just a simple reaction between hydrogen and oxygen, and it's one that I've demonstrated. I've demonstrated it with exploding a balloon. It really is quite an exothermic reaction, produces a lot of energy. So it's just a simple hydrogen plus oxygen to produce the water vapor. So very, very high energy reaction. So let's take a look at this reaction. What we're going to do is first do a gram to mole conversion. So we can't do the bridge step yet like we'd see in a stoichiometry problem because we're given a gram quantity of oxygen. So what we need to do is a step that involves the molar mass of oxygen. So I would take first my given 45450 grams of O2. Using the molar mass of O2, I'm going to divide 45450 divided by the 32. But the problem can be set up like this. And this is just doing a simple gram to mole calculation. And I get an answer of 1420. I'll put a decimal point to keep significant figures, moles of O2. And I got that from looking at the periodic table and the atomic masses. So We're going to be always using the atomic masses pretty much for the rest of the semester. So have this handy, and I just of course used the oxygen, which is 16, and 16 times 2, so that's where I got the 32. So that's my first step. My next step, because it's the relationship between oxygen and water, and I have my quantity of oxygen in moles, I can actually now do the bridge step. So I would take that 1420 moles of O2 to calculate this. I'm going to take my 1420 moles of O2, and I'm going to multiply it by the ratio of oxygen to water. And because I want to find the water, it's the water that's being asked, I'm going to put 2 moles of H2O on top of the equation, and then 1 mole of O2 on the bottom, because that coefficient in front of the O2 is a 1. And that's called the bridge step. So I took the answer from problem 1, from the first step. So my first step, getting the answer of 1420, and then the answer from that, I took that into the next calculation, which involves taking 1420 times 2 divided by 1. And again, that lets my units cancel, moles of O2, moles of O2, and of course that's just a double, so it's 2840. I'll put that decimal point again, and this is moles of H2O. And that's it. I would stop at that step because this is just simply doing a gram to mole calculation. So I started with my given gram quantity divided by the molar mass to get the moles, and then I took that mole value, did the bridge step using the balanced equation. Okay, one thing to mention as you practice these and work through these, when you do the molar mass step, don't use the balanced equation. So I would not use the coefficient in the balanced equation. So in other words, if in the balanced equation there was a 3 in front of the O2, in the first step I would not put 3 moles of O2 over 32.00 grams. That molar mass step, do not look at the balanced equation. It's only in the bridge step. So it's only in this step that we call the bridge step that we use the balanced equation. Okay? So try the next 3, and hopefully that'll get you comfortable with doing a given gram quantity, find a mole quantity. Okay, in this last calculation, the last type of stoichiometry calculation, I'm going to show you how to go from a given gram quantity C, find a gram quantity of A. And the reaction that is in the video that I'm showing that I actually did is quite interesting, because what I have in the test tube is potassium chlorate that's decomposing into potassium chloride and oxygen. And then when you put a sucrose material in there, it decomposes the sucrose. So there's actually 2 reactions going on, but we're going to investigate in this potassium chlorate decomposing into potassium chloride and oxygen. And the question reads, what mass of potassium chloride is produced with 53.4 grams of oxygen? And yeah, there's the peeps going into solution, not solution, but into the molten potassium chlorate. Peeps are highly sucrose, and they're not really my favorite candy, so this is what I like to do with my peeps. But it's really cool chemistry because you can see that colored flame from the potassium, and then also at the end of the reaction you can see the evidence of not just white potassium chloride, but you can also see some carbon, because I decompose the peeps too into carbon and water vapor. So it's quite a violent reaction, but absolutely that's what I would do with my peeps for any festive season. It's how a chemist celebrates candy for sure. So there's your carbon. So there's the carbon of the peeps. So let's look at this reaction. So we're given a certain gram quantity of oxygen. We want to find a mass of potassium chloride. We're going to definitely use some molar masses here. So I'm going to bring up the periodic table. Oh, wait, before I do that, let's highlight in the equation the potassium chloride and the oxygen, because those are the 2 that we're going to be working with. And I'm going to just kind of save myself some time, calculate some molar masses. So I need potassium, I'm going to need the chlorine, and I'm going to need the oxygen. Okay, so let me calculate some molar masses. That way we'll be ready to plug those into the calculation. Okay, so I have my molar masses. I have my molar mass of KCl and my O2, and those are the two that I'm going to need for this calculation. Well, seeing that I'm starting off with a given quantity of 53.4 grams of oxygen, I'm going to start there. So I'm going to start with my 53.4 grams of O2. And I have to do a gram to mole conversion using the molar mass of oxygen. I do this because I need my quantities in moles in order to bridge from oxygen to potassium chloride. So I'm going to just simply divide by my molar mass, which is 32. And this is a good place to also remind you, you notice how I don't use the 3O2, I don't say 3 mole O2 over 32 grams, because this is the molar mass step. In the molar mass step, I just use the molar mass. And my units cancel of my grams oxygen, and I'm left with 1.67 moles of O2. Okay, so that's the first step in the calculation, is to go from grams to moles. My next step is I can bridge. So I'm going to bridge my mole quantity of my O2 to finding the mole quantity of my KCl. And this is where I use my balanced equation to do this. So it's that ratio, that 2 to 3 ratio that I'm going to use. So I'm going to take my 1.67 moles of O2 and I'm going to bridge this. Building the bridge, so that's why I like it being called the bridge step, because it is like building a bridge. And I'm going to put on top what I want to try and find, and in this case it's the KCl. So I'm going to put 2 mole KCl on the top. And then what am I leaving? I'm leaving the O2, so I'm going to put that coefficient 3 mole O2 on the bottom. So this is the next step, and again my units cancel with this step as well, leaving me with moles of KCl. And I get with the answer for this one, 1.11 moles KCl. Okay, not done yet, but this is the second step of the stoichiometry calculation. Now for the third step. I'm going to take the answer from the second step, which is the 1.11 mole of KCl, and I could stop here if moles of KCl was being asked, but it's not. A mass or a gram quantity of the potassium chloride is being asked. So what I need to do is use that molar mass of KCl that I figured out right here, the 74.55, and I'm going to take the 1.11 and multiply that by the 74.55, and I'll put that gram KCl over 1 mole KCl. This is how I set up the calculation for the molar mass, so that my molar mass, or my mole unit, will cancel and I'm left with mass. So here I get an answer of 82.8 or 75, I'm going to round that up to 8 grams of KCl. And that's my final answer. Now one thing to be noted is if you did not clear your calculator after you did that step, so if you did not clear your calculator after doing, the answer from step 2 into step 3, you could have gotten maybe an answer of 82.999, kind of repeating, which would round that up to an 83. And that is also a correct answer. It really just depends on where you're rounding, if you're rounding after each step or if you're going to round at the very end. But based on significant figures, those are actually the same answer. So either one's acceptable. So try the next 3. Those are all the 4 types of stoichiometry problems. I encourage you to try the problems on all these pages just to enforce that you're getting a good understanding of how to do these calculations.